This is our robot, and we named it the Magic School Bot.
Here we go. 4, 3, 2, 1, go!
Every year in the summer, teams of 4 engineering physics students spend 6 weeks designing and building a robot. At the end of the summer in August, we pit our robots against each other in a 2-hour-long competition. The Magic School Bot was our team's entry in the 17th annual UBC Engineering Physics Robot Competition. The theme of this year's competition was Mission Impossibots. Our robot, actually a highly trained secret government agent, is given 2 minutes to infiltrate an enemy base and rescue our 6 captured colleagues. In the first phase of the competition, the robot must pass through an alarmed gate. By detecting the frequency of the gate beacon's infrared emissions, we can detect when it's safe to pass through. In the second phase of the competition, we approach the captured secret agents, which are actually bath toys, and rescue them from certain death. 1 point is awarded for each rescued agent. If we're too slow, the agents will be dropped into the water and drowned. After rescuing the agents, we're required to send them to safety by sliding them down a zip line. An additional 2 points are awarded for each secret agent that we manage to send to safety, for a total of 3 possible points per agent, or 18 possible points per round. In designing our robot, we followed a few guiding principles: simple hardware and multiple iterations. Our strategy relied on speed and excellent sensing and positioning. These principles led us to win 3rd place during the competition. Over 4 rounds, we scored a total of 60 points. Each of us will now say a few words about some things we would like to highlight about our robot.
My name is Cindy, and right now I'll be talking to you about the mechanical design of our robot. Our design philosophy was that we wanted our robot to be simple and easy to prototype. The simple design really helped with the line following because we got it down to be super fast and reliable, which was definitely a big advantage that our robot had. I'd say one of the biggest trade-offs is that we kept the chassis small because it would make it easier to turn, but that also meant that the basket for holding agents was smaller. We had issues at the beginning with sometimes agents would fall out of the basket because they would get piled too high and then 1 or 2 would just drop out. I think one of the other big advantages that we have is that we had claws on both sides. And because our competition surfaces were mirrored, having claws on both sides meant that whatever side we were on, we could use the claw that would give us a faster run time. Since a robot has to fit through a 12 by 12 gate at the beginning, so we start in a position like this. So, and after it moved forward, claws go up, and then they could pick up agents. And once agent retrieval is done, we make sure they're out, and then the zipline basket just goes up. And because we were driving at such high speed, sometimes we had troubles with this basket tipping over because this is so light. So how we fixed that was that we put a dot of Velcro at the back and we just Velcroed it on.
Hi, I'm Lise, and I'm going to be talking about the electrical system in our robot today. The entire robot was powered with a single lithium polymer battery, which runs at around 16 volts. And we have 2 regulators to switch the voltage down to 12 volts to power our computer and 5 volts to power the servos and the claws. We took a similar approach to the electrical design as we took to the mechanical design. We wanted to keep everything as simple as possible, and we also did a lot of iterations. I think we ended up making about 6 different sets of H-bridges. So we made all of our circuits very tiny. For example, this circuit, which every single robot has, On our robot, it's probably about 1/3 or 1/4 of the size as most other robots. The advantage is that as a result, we needed very little space for our circuits. So we were able to have this tiny robot that was much easier to control. One of the decisions that we made was to spend a lot of time at the very beginning making sure that our electrical system would be very robust. So this meant grounding and shielding all the wires, making sure that all the connectors had good strain relief. We even had to make our own shielded cables because we couldn't find the exact correct ones. This ended up paying for itself later on because we had very few failures due to broken connectors and noisy signals. One of the really cool things that we did is that we designed everything to be easily replaceable. This circuit, which from previous years we knew was one that was very prone to breakage, we had a backup always sitting in a drawer somewhere so that if one of these circuits broke, we could just throw it out, pull out the backup, and just pop it in like that.
Hi, my name is Jason, and today I would like to talk about the software of our robot. So we developed our software using finite state machines. This means we characterize the behaviors of a robot from stage to stage to stage without having one stage affecting the next. All the functionality is separate of one another. This means that on our single core processor, we can multitask and do many things at the same time. So one advantage of this would be our robot can drive along and raise the platform at the same time, and this would save us a few seconds and let us finish the course a little bit faster. Some of the trade-offs is the code becomes a little bit more verbose. Our code is over 3,000 lines long, while most groups had it under 1,000. Our team came into list competition very confident in our software skills, and that's why we had such a big emphasis on it.
My name is Amr, and I'm going to talk about the signal processing system of our robot. During the competition, the robot needs to respond to infrared signals of different frequencies. This will tell the robot when it's safe to proceed along the course. During one of our labs, we built a hardware filtering circuit that used op-amps and resistor capacitor circuits to filter 10 and 1 kilohertz signals. In this approach, our microcontroller samples the signal directly and does all the filtering in software. By using software to filter the signal, we reduced the amount of electrical components on a robot, we eliminated the need for additional batteries, and we overall have less points of failure. Initially, we were worried that running this code would take too long, but we were able to get the robot to sample and process a reading in under 2 milliseconds. It was fun coming up with a different approach to the problem, one that our course instructors were not expecting. Our filtering system was so sensitive that it could detect the beacon while the robot was still at the starting line. This allowed us to track when the gate was opening and closing. Even if the gate opened just before we started the robot could charge right through the gate with a fraction of a second to spare before it closed. Since the system worked so well, they had to ban other teams from using our code. Our robot has 2 infrared sensors, and using the difference in signal strength, we can align the robot with the infrared beacon, like so.
Okay, so the story behind the smiley faces is we decided to decorate our robot using stickers. Every time we failed at rescue an agent, we would add one of these unhappy red smiley faces, or frowny faces, and every time we succeeded, we would add a happy smiley face. So our robot is actually decorated with the story of our successes and failures.
A tool that was really helpful was a laser cutter because most of our robot is made of hardboard, as you can see. We needed to cut a lot of hardboard to make a lot of chassis. In the process of making chassis, we would usually discover that we'd made a mistake. It was too short or there were holes where they weren't supposed to be. This is chassis number 5. We got better at the process.
H-bridge. It was very difficult to solder this.
Did you say fun?
Yeah.
Oh. Like towards the camera.
Yeah. Well, step one, I guess, is to turn the thing, Tina, on. Yeah, that's start. And then you press start and it'll do the thing.
Okay, cool. Oh, robot, don't die on me. Yeah, no, that's the most important one. Only other ones have been doing anyways.
If you could cut power to the servo somehow, like this is pretty much perfect.
I don't know.
It's already rolling.
Oh!